All right, good morning. It's time for us to get started. You guys seem so wide awake today. I'm going to try to end that shortly. Just kidding. All right, if you guys could keep it down, I'd really appreciate it. All right, it's 10 o'clock. All right, so exam 1 is 6 days from today. There'll be a review session on Friday and Sunday. Please keep it down. All right. I've got enough, little things speaking in my head. I don't need them externally too. All right, that was a joke. All right. I will not come into class with an axe. That's what I tell myself. Anyways, all right. So things to bring to the review sessions. Please have questions. Right, make it your own. So if there are things that you need clarification on, this is the time to get things straightened out. And then in the absence of having questions, the TAs will go over the review worksheets and the practice exams. So bring the hard copy. Be prepared to work, right? That's how you learn. Right. Last time we met, we introduced the Lennard-Jones potential. That tells us the interactions between two different molecules, or if we're talking about gases that are monoatomic, the interactions between those. We have the term that's associated with attractive interactions and repulsive interactions. We also looked at the difference between our real molar volume and the ideal molar volume and the limit of low pressures. And what we found was that that's the same as the second virial coefficient. So it gives us a nice physical understanding of what the second virial coefficient gives us. We went over the equations for dipole-dipole, dipole-induced dipole, and London dispersion interactions, and then we related that to the Lennard-Jones potential and then to the second virial coefficient equation. All right, so what we're going to do today is we're going to finish off our chapter 2, where we started our discussion of the potential, simple potential, hard sphere potential. We're going to look at one that's a little bit more complicated, but it's still simple, and saw what we could get from the second virial coefficient. From there, we're going to go into Math Chapter B. That'll be statistics, and then from there to Chapter 3. So in statistics, hopefully some of this is review, and then for Chapter 3, just a little bit of a heads up. That's likely to be new to most of you, and it can be a little bit confusing. So Chapters 3 and 4 might be a little bit more challenging intellectually. Okay, so last time we met, we were basically looking at the hard sphere potential. But what we said was we couldn't get our two particles closer than the sigma distance between. And we said that that sigma is related to 2 times the radius of our spherical particles. And then beyond that point, we have no interaction at all, so the potential is equal to 0. So it's important to recognize that when we go to our more complicated potential interaction, this portion will be identical. So we're going to be doing an integration from 0 to sigma. So we expect that we're going to have the same output. And then we're also going to see a region where we have no interaction between the two particles, and we expect to see that integral be the same, which we've shown previously is equal to 0. All right, so where we left last time, basically we found that our expression for the second virial coefficient was given by this 2 pi Na sigma cubed over 3. All right, and then to try to relate this to the volume of our molecule, what we recognize is that's 4 times the particle or molecule volume, and then times the number of particles, which is Avogadro's number. Okay? All right, so this clearly tells us that this second virial coefficient is related to the size of our particles. All right, make sense? Okay, so now, the other thing that we pointed out was for this hard sphere model that works at high temperatures, it's repulsive interactions only. So what we're going to do is we're going to tweak the model a little bit and say, what about attractive interactions? So that's going to give rise to our square well potential. So in this region, we have a hard sphere. So the potential is equal to infinity. All right, so let me just write a few things here. 0 to sigma, the potential will be given by infinity. All right, We'll write that in there, and we know that the exponential term for the second virial coefficient will then be e to the minus infinity over kBt, which is equal to 0. Right? And this is why I said we should pay attention to the previous integrals, because this will be exactly the same, right, for the hard sphere potential. Right? Then we have this little region where we have attractive interactions, right? And we define it, just consistent with the textbook. So the well starts at sigma, and then it goes out to lambda sigma. So that's just the width of our well, okay? All right, so in this region, our potential is going to be equal to minus this energy, right? So minus E. Right? And that means we're going to need to integrate from here, from sigma to lambda sigma. And our exponential term will be e to the minus e, which will be plus e over kBt. Now, I can't do any further simplification of that, so that means we're going to have to think about how we're going to integrate that. Okay? And then beyond the well, our square well, then we have no interactions again. And this will be the integral from lambda sigma out to infinity. And in this case, our potential is equal to 0. Okay? And what we've seen previously is that that integral goes to 0 because we have no interactions between our particles. Right? Keeping in mind that the second virial coefficient is reflected by the interactions between particles. Right? So that last region, the potential will be equal to 0. And then we have e to the minus 0, which is going to be the same as 1. Okay? All right, so because we have three regions with distinct potentials, we have three integrals to worry about. The first integral is exactly the same as the integral that we saw in the previous case. So that means I'm going to just bring down 2/3 pi Avogadro's number sigma cubed. Okay? That make sense? All right? And then this last portion, we've shown previously that whenever we plug in 1 for our potential, it goes to 0. So that last portion will be a contribution of 0. Okay? All right, so we do need to pay a little bit of attention to the new part of this model, which is the attractive interaction. So that's this integral. Okay? All right, so we're going to be integrating from sigma to lambda sigma. That's over the well width, right? And then we've got the exponential of the energy of attraction between these two particles. All right? Now this looks a little bit complicated, but one of the things that we recognize is that this energy of interaction between my two particles is going to be a constant, right? And so that whole thing can come out in front. Right? So this will become ditto minus 2 pi Avogadro's number e to the plus energy of the well depth, kBt. Right? And in chapter 3, we'll see the origin of that exponential term times the integral from sigma to lambda sigma of minus r squared dr. And I forgot the integral. Oh, no, I didn't. Okay? And we already know that the integral of r squared will be r cubed over 3. And so what we can do is we can say this will become r cubed over 3 evaluated from sigma to lambda sigma. Right? And so basically that means that I need to cube this and then cube that and take the difference between the two. Yeah? The r squared is negative. No, it is, where did I do that? I pulled that out. It should not be. Okay. Thanks. Keep me honest. Let me double check my notes there, make sure I didn't screw something up, but it sure looks like that is correct. Okay. Yep. All right. So that's positive r cubed over 3. And that will become lambda cubed sigma cubed minus sigma cubed over 3. Okay? All right, so now what I'm going to do, I'm just going to rewrite all of this, and we'll see if we can simplify it a little bit, because there's a lot of things being written around. So I'm going to write equals 2/3 pi Avogadro's number sigma cubed. Right, that comes from the hard sphere potential. Right, and then I've got minus 2 pi Na. All right. Now I'm going to do something here. I notice that I've got sigma cubed in 2 places, so I can pull that out front. Right. I've got 1/3 in here, so I'm going to pull that out front. 2/3 sigma cubed. And then what I'm left with is e to the plus e over kBt minus 1. Okay? All right. So we see that we've got the same thing here and here, so I can pull that out front. So 2/3 pi Na sigma cubed times the quantity 1 minus e plus, oh, and I forgot something again. I'm trying to go too fast, which means I'm basically screwing things up. Right? I left out lambda cubed minus 1. Because when I pull sigma cubed out in front of this, I'm left with lambda cubed minus 1. Okay? All right, so now I have an expression for the second virial coefficient. So let's just talk about this a little bit. So if I have no attractive interaction, this is going to be equal to 0, right? And then that's going to make this go away. This will be 1 minus 1 or 0. And that means this portion of this goes to 0, and I'm left with the hard sphere, right? So the other time that that becomes true, if t is really, really large compared to that energy, right? If kBt very large compared to the energy, this will be essentially e to the 0, which is 1 minus 1. And again, at high temperatures, we collapse down to the hard sphere potential. Okay? Does that make sense? Okay? All right, so then the question is, well, how well does this model do? And think about what we've done. We've basically put together a very simple potential interaction, right? And that's shown in this next graph. So what we've got is the square well potential for the molecule nitrogen. We're looking at the second virial coefficient as a function of temperature. These small circles on here are experimental in nature. So that's what you would measure in an experiment, looking at compressibility as a function of pressure, okay, which we've talked about previously. The smooth curve is going to be the least squares fitting of that equation to this experimental data. And what can you say about the agreement? It's very good, right? Okay, and of course, how many people have done least squares fitting? Right? Nobody? Well, you do whenever you fit lines, right? So it's the same sort of thing. You allow some of your parameters to vary. So in this case, what we've allowed to vary is the energy E, the width of the interaction, and sigma. Right? So there's 3 parameters that are allowed to vary. So I'm just going to write least squares fit, and the parameters will be the energy associated with the interaction between our particles, the attractive interaction, sigma, the size of our particles, and then, what was the last one? Lambda, the width over which we have attractive interactions. All right. All right, so that smooth curve is calculated B to V. Okay? All right, so if we do this sort of an analysis, then we end up with an energy and a sigma and a lambda. So that means that by looking at the experiment, fitting this to this data, we can say something about the attractive interactions, something about the size of the molecule, and something about the the distance over which we have attractive interactions. Okay? All right. Any questions about that? So that last portion was just designed to help you understand the relationship between potential energies by using some simple potential energies to calculate the second virial coefficient. All right? All right, so we don't have enough time to talk about this in any depth, but I do want to just bring this back to our equations of state that are cubic with respect to molar volume. So that would be the van der Waal equation, the Redlich-Kwong equation, and the Peng-Robinson equation. Right? And because we have these parameters A and B, alpha and beta in each of these, we know those are related to the size or repulsive interactions, and A is related to the attractive interactions. That tells us that we should see a relationship between those parameters and the second virial coefficient. Right? So in all cases, B2V can be written as a function of A and B, big A and big B for the other equation state, and as alpha and beta. All right? And again, I wish we had a little bit more time, but this would take at least another lecture to talk through. We just don't have the time, right? Any questions about anything that we've covered so far? All right, so in this next section, we're going to be talking about statistics. Okay? All right, so I think what I'm going to do is introduce some terminology. N sub j and n. N sub j is the number of times we observe outcome j. So we'll say number of occurrences okay? All right, to try to put this in a little bit of perspective, I'm going to pretend that we have a four-sided die. One side's got 1 on it, 1, 2, 1, 3, 1, 4. All right? And so n sub j refers to, if this was n sub 1, that's the number of times that I roll it and I see 1. All right? If it's n sub 2, that's the number of times that I observe 2. Does that all make sense? All right? Now, if I want to know and then n by itself is the number of observations that we've made, total. Okay? If I want to get from n sub j, the number of occurrences of a particular outcome, and the number of observations total, how do I get to the probability? I divide one by the other. What's in the numerator? So I'm going to put n over n, right? And nj over n. Does that make sense to everybody? All right. If you could pass the box over there. Thanks. All right, and because we want this to be an equality, right, what needs to be true about n? It needs to be a large value, right? And so it's really the limit as n approaches infinity. All right. And after the box, if it could go back over to that table, that would be great. Okay? All right, so let's talk about our four-sided die. What's the probability that I expect to observe 1? 1/4. We agree? And what's the probability that I observe 2? It's the same. And these are all the same, right? Okay, so I wanted to introduce a relatively simple model to help get a little bit less abstract discussion. Okay? Okay, so the other thing that we need to keep in mind is that for the probability to mean anything, the probability summation has to be equal to what value? It has to equal 1. Okay? So what we can write is that the summation over I equals 1 to the number of observations of the probabilities of each of the outcomes is equal to 1, right? That's pretty important to recognize. Otherwise, our probabilities don't make sense, right? Okay, so then we can ask the question, how can I determine from a probability what the average value is, right? And so what I want to do is just think about our four-sided die, right? So for my four-sided die, if I want the average value, right, and I just want to point out that when we use these little brackets, that means average. Okay? How many people have seen that before? Okay, so that's fairly common. All right. So in terms of the probabilities, I can say that my chances of seeing 1 will be 1/4. And if I want the contribution to the average, I'm going to multiply that by the value 1. All right? And then I'm going to do the same thing for outcome 2. I'm going to multiply that by the probability. All right? And then 3 times the probability of observing 3, and 4 times the probability of observing 4. And that's going to give me my average value. Does that make sense to everybody? Okay? All right, and that's going to come out to be 2.5. We're going to use that number in a little bit. All right? So basically what that tells us is that if I want to know the average value from probability distributions, I can determine it by taking the summation over all of the possible observations, the probability of each individual observation times the value of that observation. And that will give me the average value that I expect to see. Make sense? Okay? All right, so I want to take a moment to write this a little bit more generally. All right? So if I'm interested in the average value of something that's a function of x, I'm going to use the probability. I'm going to sum over all the probabilities, and I need to multiply it by whatever that function is. Does that make sense also? Right? That's pretty critical to remember. Right? So that's going to be the summation, I equals 1 to n. So looking over all possibilities, the probability of x sub I times the value of our function that we're interested in taking the average of, evaluated at that observation. Okay? All right. So that's in general true. All right. So coming back to our probability distribution, this average value is called the first moment. How many people have heard that term before? A few of you. So that's the first moment of the distribution. Okay? All right. And then what we're going to do is we're going to say, well, what's the second moment, right? And that tells me that that's because the way I'm calculating it, I'm taking my probability times my observation squared. That means that if I sum over all of the possible outcomes, that's going to be the average squared value, right? So for our example, that's going to become 1 squared times 1/4 plus 2 squared times 1/4 plus 3 squared times 1/4 plus 4 squared times 1/4. And that comes out to be equal to 7.5. Okay? All right, so this gives us our second moment for this four-sided die. Okay? All right, so before we go forward, I just wanted to point out something. You might think, all right, so that's again the average square value. You might think that if I take the square root of that, I'm going to get the same as the average, right? And that doesn't come out to be the case, right? So I take the square root of 7.5, that comes out to 2.7. That's clearly not 2.5, right? And what we can say is that, and we're going to show this in a moment, that in general, the second moment, the average squared value is greater than the average value squared. All right? So we're going to prove that in a little bit. Okay? All right. And before we go through the proof, what I want to do is just look at, a simple distribution to see why they're not equal to each other. All right? So let's say that I have a distribution that looks like this, where it's centered around 0. Right? What's the average value for that distribution? It's 0. So x average equals 0. Right? Now, if I look at the squared value, all of these become positive, right? And so that tells me that the average square value has to be greater than 0. Okay? All right, so the other thing that we'd like to talk about is the variance. How many people have heard of variance before? A number of you. Right? So that's sigma squared x, right? And then what that refers to is the difference between our observation and the average value. We're going to take the average, right? So if you think about taking the average value of the difference between our observation and the average, that's going to, in general, be equal to 0, right? So in order for this to have some meaning, we need to square it. Okay? All right, so that's our definition of the variance. It is the square of the deviation of our observations from the average value. Okay? All right, and then the thing that you've probably all of you have heard of is the square root of the variance. Does anybody know what that's called? That's the standard deviation. Okay? So if I'm interested in using my probability distribution to determine the variance, that means that I'm going to take the probability of an observation times this function and sum over all the possible observations. Okay? So we can say that our variance will be equal to the summation over j equals 1, total number of observations. We've got the probability of an outcome. So rather than saying p of x sub j, I'm simplifying that and just saying that's observation j. Okay? And I need to multiply that by the deviation of my observation from the average squared. Okay? So again, the average value of my function is going to be that function times the probability summed over all the possible outcomes. Make sense? All right. So what I want to do is just take a moment to see if we can simplify this a little bit to see how we can calculate the variance on one of these probability distributions. All right. So what I can do is I can square this, right? So that's going to give me x sub j squared. It's going to give me my average value squared, and then 2 times the product of the first and last term, right? Okay, and then multiply through by probability. That's what I've got over here. So that's my first term squared. This will be my last term squared, and then 2 times the cross terms. Right? Multiply through the probability. So I've got a summation over all of those states. Now this is a summation of sums, which means I can separate these into separate summations. We agree? All right? And that's what I've written down here. So let's take a moment to look at these a little bit. All right, so that first term, what I see is I've got a probability of each of my outcomes times the observations, right? And so that's going to be the same as, help me out. Nobody knows? It's going to be the second moment. Thank you. Okay? All right, then we look at our next term, and what we recognize is for our distribution, this average is going to be a constant, so I can pull it out front. So this will be the summation of x sub j times the probability of this outcome summed over all the possibilities. That gives me this, which is the first moment, or the average. Okay? All right, and then my last term is going to be my average value squared, which is a constant. I can pull that out in front of the summation, and that gives me the square of my average times the summation over all the probabilities, and the summation over all the probabilities has to be 1. Okay? All right, so we end up with this term, and then we can do it a little bit, we can simplify it a little bit further. We can say x squared, so my second moment minus my first moment squared gives me the variance. Does that make sense? Okay? All right, so I want to take a moment to prove that this is in general true. All right? And so what I want to do is just point out, if I look at this value, or if I look at this value, x minus, so my observation minus my average value squared, that's always got to be positive value, right? So this is always greater than 0. Okay? And that tells me that after I go through all this derivation, that this quantity also has to be greater than 0. We agree? Right? And that tells me necessarily that this will be greater than this. All right? So we've proven that. Okay? You on board? All right. Okay, so that was for discrete probabilities. So this works for things where I have integral values of observations. So 1, 2, 3, etc. Right? Now we also know that sometimes probabilities are continuous. So if I'm talking about measuring mass, right, I don't see everything in terms of kilograms. I can have 1/10 of a kilogram, 1,000th of a kilogram, etc. Right? And so those probability distributions are continuous functions. All right? And so for continuous functions, we need to define how we talk about probabilities. So I can say the probability of x dx means the probability that I have an observation between x and x plus dx. So the probability that the observation is the range of x to x plus dx, right? And that tells me that if I want to know a finite probability, what do I need? What mathematical operation do I need to perform on this probability dx? I need to integrate it. Okay? All right, so that leads us to saying that the integral from a to b of p of x dx is the probability that our observation is in the range of a to b. Okay? All right. So the other thing that we need to keep in mind, and that is that just like what we saw previously, for my probability to have meaning, it has to be normalized. So that means the sum over all the possibilities has got to be equal to 1. Right? So that's what we call our normalization condition. All right, so our normalization condition says basically looking from minus infinity to infinity over all the probabilities has got to be equal to 1. Okay? All right, now when I use this particular equation, this says that my observation can be positive or negative. Now some experimental quantities are only positive, all right? So for instance, if we're talking about mass, radius, volume, x is always greater than 0, okay? Or greater than or equal to 0. And that means that we don't integrate from minus infinity to infinity, but we integrate from 0 to infinity. So I'm going to say p of x dx. And that will give us a summation to 1. Does that make sense? Okay? All right, so now that we understand probabilities for continuous functions, what we want to do is define our first moment, second moment, and variance, right? And so it's going to be very similar to what we did for our discrete probabilities, but we're going to replace the summations with integrals, okay? So the first moment will be 0 or minus infinity p of x dx times x. Okay? And that will give me my average value. Make sense? And then my second moment will be integrated from 0 or minus infinity, depending on what our observations are, p of x dx. And what do I need to multiply the probability by in this case? X squared. And that will give me my second moment. Right? And then if I'm interested in the variance, then we use our definition of variance. Right? So this will be the integral from 0 or minus infinity to infinity of x minus our average value, that quantity squared, times the probability dx. Okay? And that gives us the variance. And if I'm interested in getting the standard deviation, I know that all I need to do is take the square root of that integral. Okay? All right, so what we've talked about up to this point is pretty abstract. So I want to do a quick example of something that's a little bit more concrete. So we're going to look at a Gaussian distribution. Gaussian distribution is also known as a normal distribution or a bell curve. Okay? All right, it has the functional form of this constant times e to the minus x squared over 2a squared, right? And as we've defined it, we can have negative values. So this is what it looks like, all right? So I can go from minus infinity to plus infinity, okay? All right, so this is the functional form, and what we want to do is get an expression for the standard deviation, and we want to get what this normalization constant is, okay? All right, so the normalization condition for this will be, all right, the integral from minus infinity to infinity of c times our function e to the minus x squared over 2a squared dx, and that has to be equal to 1. Okay? That makes sense? All right. And we recognize this is a constant, so we'll be able to pull that out front. We want to go about integrating this. This doesn't look pleasant to integrate. So what I do is I go to some integral tables, and I see something that looks like it's close, right? Exponential to the x squared, right? And then this alpha will just be 1 over 2a squared, which is what we say down here. Does that make sense? The other thing that we recognize here is that we want to integrate from minus infinity to infinity, but we only have 0 to infinity, okay? All right, so one of the things that we recognize is that this particular function is symmetric about the origin, right? So if I integrate from here to here, that's going to be the same as the integral from here to negative infinity, right? What kind of a function exhibits that property? What's that called? How about an even function? You heard of that? Yeah? All right, so even functions. How many people have heard of even functions? All right. So what tells me that I have an even function? It's symmetric, but numerically this is saying f of x is related to f of minus x. All right? So if that holds true, I have an even function. All right? And what we can say for an even function is that the integral from minus infinity to infinity f even x dx is equal to 2 times the integral from 0 to infinity for that even function. All right. And again, that's because we're symmetric about the origin. All right, so basically that tells us that we're good to use this integral from the integral tables. Okay? All right, so next up, we want to find the normalization constant. So we're going to do this integral, right? We know that that's equal to 1, all right? And that's going to be equal to 2c times the integral from 0 to infinity of e to the minus alpha x squared dx. And the table of integrals tell us that this will be the same as pi over 4 alpha to the 1/2, right? We can do a little simplification here. What's the square root of 4? 2. So that means my 2's go away. All right, so I can cancel those. All right. And then I can, whoops, I canceled the wrong thing. Sorry about that. 2. All right. And so what I can say then is c is going to be alpha over pi to the 1/2, which is the square root. And at this point, I can substitute back in for alpha. So we've previously said in order for us to apply this integral, alpha has to be 1 over 2a squared. And so that means that our constant of normalization will be 1 over 2a squared pi square root. Okay? All right, so at this point, I have a normalization constant, and now I can determine first moment, second moment, and variance. Okay? So the first one that we're going to do is we're going to ask what the average value is. All right? So we have our probability distribution, or our probability function. So I've got my normalization constant, and then e to the minus x squared over 2a squared. Okay? All right. And then if I want to know what the average is, I'm going to look at the integral from minus infinity to infinity of 1 over 2 pi a squared square root e to the minus x squared over 2a squared dx. And what else do I need to put in here? This is all I've done is I've got the integral of the probability. So if I integrate this, we know that's going to be equal to 1. All right? So to get the first moment, I need to multiply the probability by x. All right? Okay, so if I look at this and I ask the question, is this an even function? F of x relative to f of minus x, what's the answer to that? Right, so if I put a minus 1 in here, that gets the same thing as a plus 1. But if I put a minus 1 in front of here, that gets me the negative of plus 1. Right? So that means it's going to be f of x equals the negative of f of minus x. And so I don't have an even function. What do I have? I have an odd function. All right? And what do you know about odd functions integrated from negative infinity to infinity? They're antisymmetric, right? So this summation will be equal to the absolute value of this summation, but because they're opposite sign, it goes to 0. Okay? So we'll say antisymmetric. And the integral from minus infinity to infinity of an odd function equals 0. Okay? All right, so that also tells us what's our average value. It's going to be equal to 0, right? And of course, we could have seen that if we looked at our original function, right? We saw that it was symmetric around the origin. So this has to be the average value. Okay? Make sense? All right, so we now know what the average value is for the bell curve or the normal distribution. Right, next up, what we want to do is look at the variance. Okay? So for the variance, we know that we're going to have to integrate over all space. So we've got the definition of our variance, x minus the average value squared, times our probability. Right? So this looks, and then I put in my probability what we've derived. Okay? All right, so that looks like it might be a little bit complicated, but what we recognize is we've just determined that this value is 0. Okay? All right, so what we can do is say, I'm going to pull out my constant out front, so 1 over 2 pi a squared to the 1/2. I'm going to integrate from minus infinity to infinity x squared times e to the minus x squared over 2a squared dx. All right? Okay. Is this function an even function or an odd function? I have an even function. Okay? And again, we don't want to do the integration. So we go to a table of definite integrals. We find a function that looks similar. So I have x squared exponential to the x squared. And we've got our alpha. That alpha is the same as the alpha that we've previously introduced, 1 over 2a squared. Right? And our table of integrals tells us that this is the integral from 0 to infinity. Okay? So I just brought that over here. Right? And that gives, if I substitute in for alpha, 1 over 2a squared, that gives me this relationship. Right? So recognize that this integral only refers to 0 to infinity. Okay? All right? And what I need to keep in mind is that if I want my variance, I need my constant, and then I need to say 2 times the integral from 0 to infinity. Okay? All right, so let me do that. So sigma squared, there's my constant, 1 over 2 pi a squared to the 1/2. Multiply by 2. Right? And now I can bring in my integral. That's going to be a squared over 2 times 2 pi a squared to the 1/2. Right? Just want to make sure this comes right into there. Okay? All right, so we should be able to simplify that at this point. All right? So we see the 2's cancel. We see that 2 pi a squared to the 1/2 cancels with this, and I'm left with a squared. All right? And so what we can say for this probability distribution is that we've got 1 over 2 pi, not a squared anymore, but this is going to be in terms of our variance, to the 1/2 e to the minus x squared over 2 sigma squared dx. All right? And this is one of the reasons that people like to use the bell curve, is that intrinsic in it is the variance, which means you can get the standard deviation. Okay? Make sense? Let's see, where are we at? 1049. This is probably a clean place to stop. All right, so we'll leave it there. We'll see you guys on Friday. Have a good afternoon.